Welcome to part 3 of our solar troubleshooting series. In this part, we're going to talk about electrical testing. So in parts 1 and 2, we talked about the overview of the solar system types, mounting, and other important background topics. We talked about the visual inspection of the system in part 2. If you have not watched parts 1 and 2 yet, please do so. All of these parts are arranged in a way that are for safety purposes and as well as making sure you do not miss anything. They build upon each other. So for an electrical solar inspection, once you have completed your visual inspection, the electrical inspection is next. How I normally approach systems is from the farthest point from the panels working towards the panels. For most inspections, I use 2 readings, voltage and amperage. Your meter must do both AC and DC for voltage and AC amperage. For larger systems, you may want to consider a DC amp clamp. Don't attempt to use inline amperage readings or your meter will be damaged. The amperages are just too high. Just a word of warning before you look at DC amp clamps, they're expensive. So we're going to start off by looking at the AC voltage and AC current at the breaker that feeds the solar system. Then we're going to look at the AC voltage and current at the output of the inverter or the combiner box for micro inverter systems. Then we're going to start looking at DC voltage for each array and work our way back towards the panel. If there's AC voltage and a current over 3 amps at the inverter side of the solar breaker or disconnect, the inverter is producing power to some extent. If there's AC voltage at the output terminals of the inverter or the collection box along with current of over 3 amps, the inverter is producing some power. For collector boxes, there should be AC voltage and current coming in from each AC circuit from the panels. If there's DC voltage on each array in the string inverter, then the wiring is good. If there's DC voltage and no AC current, then the inverter's not operating. Step 1. Test AC current and voltage near the distribution box panel or the disconnect on the output side of the inverter or collector box. In other words, the voltage between the collector box or inverter and the breaker panel. If there's no AC voltage, check the breaker. See, here's the thing. This portion should always have AC voltage. It's connected into the grid. If you have power to the building, you have power on this circuit. If there's no voltage here, you got to find out why before you go further. If the current is under 3 amps, move on to the inverter. If the current is over 3 amps, hey, your inverter is actually doing something. Check the DC side at the inverter for all arrays. The reason I use 3 amps is because an inverter will actually use a little bit of power when it's not producing power. You can't tell with a standard amp clamp which direction the power is going. So in these pictures, we're taking the AC amperage at the distribution point. Okay, we have the red wire, I'm going to call it line 2 to 20.35 amps. Okay, and then we also had another panel or another inverter, 19.06 amps. Okay, I have 2 inverters producing power. Is it right? We don't know yet. I also have 245.8 volts at that area. Again, this is the AC amperage at the distribution point. Then I move over to the disconnect. Okay, what's my amperage and what's my voltage at the disconnects? 245 on both sides, and my total amperage is 37.12. Not bad. I'm happy with that. Then we're going to go to the AC voltage and current at the output of the collection box and or each inverter. Again, collection box for micro inverters, inverters for string. If over 0 and under 3 amps for a string inverter, check the DC side. Check the rated voltage amperage for each microinverter and verify against the rating. Make sure you take solar conditions into account. Take a quick look at the sky. Are we partially sunny, 75%, 80%, full sun? Okay, It's very difficult to inspect a solar system under 50% or more than 50% cloud. Okay, just be cautious on that. So in this one at the inverter, I'm looking at each leg of the circuit. L2, I have 12.8. L1, I have 13.7. Okay, so a little off balance, but not bad. And there could have been a cloud that went over while this was going on. I'm going to take a look at the AC voltage. Some of these are hard to get the probes to hold in there. Be cautious because you can get arc flash here. Just be aware of that. Between line 1 and line 2, I have 245.8. Few safety notes here. The remainder of these steps are dealing with direct current at higher than normal voltages. Most people think direct current, 12 volts, battery power from your car. This is much higher voltage. The average solar system, each array is going to be over 300 volts DC and 30 amps. Larger systems can be running 600 volts and 60 amps or higher. These voltages and currents can kill you. Be careful where you step, be careful what you touch, and make sure your meter can handle the voltages and amperage. Read the manual on your meter. Make sure you can put your meter on a 600 volt or higher circuit on the DC side. So next we're going to check the DC voltage at the inverter. For each array, check the DC voltage coming into the inverter. Verify that all DC disconnects are on. Verify the inverter solar disconnect is on. Most inverters has a disconnect on it someplace to disconnect the solar side. If 0 volts DC, check the wiring. It is highly unlikely, again, let me repeat, it is highly unlikely that all panels have failed. Check the connections. It's likely one is open or a crimp connection has failed. These panels are going to be producing something. Okay, someplace in here you have an open circuit if you have 0 volts DC. Okay, so again, we're going to put our meter to DC and we're going to check the voltage on each array. This inverter has 2 arrays out of 3 that are wired. So you're going to go from A plus to A minus. Again, positive and negative matters. On the left picture, I have 141.2 volts. On the right picture, I have 337.4 volts. The way these arrays are laid out, those numbers make sense. Okay, just another type inverter, going to do the same thing. Okay. Going to do the same thing. The one on the right is not operational. I basically, it's somewhat, there's problems here someplace because I have 1.8 volt DC on that. I'm going to be looking at those panels. I still have a good circuit because I have voltage, but there's something going on someplace. Then we're going to go check for step 4, we're going to go check the DC voltage at the array. Okay, you're going to find a place to get into the DC wiring. A lot of times it's great if there's a disconnect or a wiring connect, and you're going to check the DC voltage at the array. This array had 251.6 volts. It was almost 50 to 70% cloud cover on the day where I did this inspection. So again, the number made sense. Remember, voltage is the variable based on sun coverage, okay, that you can measure. The higher the cloud cover, the lower the voltage. The more sun, the higher the voltage. Voltage will vary it's a series circuit. Then you're going to check individual panels. This is your final diagnostic electrical step, is to check individual panels using a panel tester. Read the manual for your tester. They will burn up if not used properly. Most only will check one panel at a time, so don't install your solar panel tester on the entire array. It can't handle that voltage. On a roof array, it's going to be a challenge. You might have to lift panels to find the proper wire connections. Think about safety. It's doable on a ground array because you can get right under the panels. This is an example of a panel tester. Okay, the one on the left, I'm producing 5.61 volts. Okay, again, partially cloudy day. Okay, low power. It made sense based on the tag, based on the rated output voltage. Okay, the one on the left, I have 13.7 watts, only 21. It's tough to tell with that. It might have been 1.1 volt, and current was 0.65. Again, based on cloud cover, based on panel condition, it sort of made sense. So if you have AC voltage at the breaker, disconnect and inverter AC terminals. The wiring is good, the breaker's good, and the grid is providing power. If you have amperage over 3 amps between the AC terminals of the inverter and the breaker, your inverter is producing some power. Most inverters will consume a very little power during the dark periods without solar radiation. And again, your amp clamp can't tell which direction that current is going most often. Okay, for microinverters, I wanted you to just not worry about the next two slides. For microinverters, you'll not have long lengths of DC wiring. The only DC wiring is out of each panel and directly into the inverter right on the roof. Check all the connections if you have problems. Most times, these problems are bad connections. If you have DC voltage at the input terminals to the inverter and the wiring, that means the wiring is complete between the solar arrays and the inverter. Remember, any break in a series circuit will provide 0 volts where you're checking. Okay? Think about the old style Christmas trees lights. A light bulb went out and the entire circuit dies. If you do not have DC voltage, it will be a wiring issue. It is rare that all the panels in an array fail at the same time. Trace this the way you would any other open circuit. Check the connections first. Those connectors fail. If you have DC voltage but it does not seem high enough based on the number of panels, size of array, age, and cloud cover, you need to evaluate each panel. If you have DC voltage and no AC output current, then the inverter is the problem. Look for fuses. And also, sometimes shutting all power down, that includes both AC and DC, to that inverter and bringing it back online will reset any safety trips. Be aware, the newer inverters have GCI, GFCI, and arc fault checking on the DC side. It is very possible that there's an arc fault hazard someplace in the DC wire. That's why it's so important to inspect those. Using a solar panel tester and check for output at each panel is the way you do testing results on panels. If you don't have a solar panel tester, make yourself a connector set so that you can plug your DC voltmeter into each panel to check for voltage in the sun. A panel with 0 volts or much lower than the data plate is damaged. A panel with close to rated open circuit voltage with good sun coverage is good. If there's solar optimizers on the panel, disconnect the optimizer and check for voltage at the panel without the optimizer. If you have voltage at the panel without the optimizer and no voltage with the optimizer has failed. And then to wrap up part 3 of the electrical testing, okay, our inspection used DC, AC, and amperage to locate the source of the problem. Working in from the breaker. You want to work from the furthest point away from the panels back to the panels. Solar panels themselves are not repairable and has to be replaced. Solar inverters are very rarely have serviceable components. Wiring can be fixed. Connectors can be fixed. The most critical part of the electrical testing is to do it the same way every time. Record your results as you move through the process. In the final part of this series, we're going to look at the repair-replace options that make sense and talk a little bit about them. And time for my standard disclaimer. The opinions expressed in this presentation are my own and are not those of my employer. If I say something you disagree with, blame me, not my employer. And to repeat, this is not a presentation designed for the do-it-yourself owner. There are serious safety concerns when servicing a solar system. Only do so if you're properly trained in electrical and ladder safety.